Okay, got it. All right, we're back. We are looking at solving radical equations, right? So last class, we talked about the fact that we want to isolate it on one side, and then because we had square roots, we would square both sides to cancel out the square root. Okay, cool. The only thing is, we didn't really get into anything that was actually a little bit complicated. Like the stuff that we saw was really not that bad. Like when you think about it, big picture, and you look at each of those problems again, they're really not that bad. You isolate the term with a radical, you square both sides. Maybe you have to square a binomial, which means you write it out twice and you distribute and then you move terms around. Okay, cool, no big deal. But if you look at page 29, then you see that this is actually interesting, and this one's a little bit more complicated for sure, which is why you have an entire page to do this problem. So I wanted to show you what happens if you have two radicals in your equation and you want to solve. Check it out. We have 4x plus 5 under the square roots plus square root of x plus 5 is equal to 3. Think about the steps that you were given yesterday, last class, which was on one side of the equals, isolate one radical so that everything else is on the other side. What that means to all of us is that we want to take, for instance, this radical here, because this is one whole term, okay, it's minus the square root of x plus 5, and bring it over to the other side. That's exactly what we're going to start with. So subtract square root of x plus 5 on both sides. So this is one term that goes away, right? It's a group, it's an entire expression, moves over. That leaves us with square root of 4x plus 5. Ooh, I don't like that pen. Let's try this one. Is equal to 3 minus square root of x plus 5. Okay, you essentially want to get one radical alone on each side in this case. Because I want to eliminate my square root, it would make sense I've got to do the opposite, which we all know is to square. Check this out. You're going to square both sides like this. Notice here, this one's not a big deal. The square root of 4x plus 5 squared, because the square root is over the entire expression, the square root and the square cancel each other out, and that leaves you with just the 4x plus 5. That's not a big deal. What's very interesting is what's happening over here. In my parentheses here, I actually have a binomial. So I'm squaring a binomial, which means, guess what? I've got to write it out twice. All right, check this out. Let's do some side work. Shift this over. We have 3 minus the square root of x plus 5 times 3 minus the square root of x plus 5. All right, let's distribute. Just like we did before, don't overthink it. 3 times 3, well, that's going to give us a positive 9. Then we have 3 times negative square root of x plus 5. 3 times negative square root of x plus 5, it's 3 times this expression. So it's going to be minus 3 square roots of x plus 5. Next, we have, again, the same quantity, so minus another 3 square roots of x plus 5. Then we have a negative times a negative is a positive. Square root of x plus 5 times square root of x plus 5 is just x plus 5. Don't forget that idea. When you take the square root of x plus 5 and you multiply it by the square root of x plus 5, these square roots cancel and leave you with just the x plus 5. Think of it as square root of x plus 5 squared, right? Okay, got it. Let's clean this up. So we have 4x plus 5. By the way, if you do have questions and you're like, I know you're saying got it, but I don't got it, just let me know. I'm totally happy to break stuff down. Like for real, for real. Don't ever feel like nervous about that. We have a 9 and a 5. I'll put those together. That's 14. We have an x here, so I'm going to write plus x. And then I have negative 3 of these guys and another negative 3 of these guys. So now I have a negative 6 of these guys. Sometimes I like referring to that expression as like a package deal so that you can kind of get a sense that all we're doing is combining the coefficients. That's all we're doing. You have negative 3 square roots of x plus 5, another negative 3 square roots of x plus 5. So that must mean we have negative 6 square roots of x plus 5. Okay, cool. So we still want to focus on isolating the radical because guess what? We have another one. So we want to slowly get this term by itself. To do that, I'm going to subtract 14. I'm going to subtract that x. And that's going to leave me with 4x take away x is 3x. 5 take away 14 is negative 9. Notice this cancels out because they're opposites. These cancel out because they're opposites. And then you have negative 6 square roots of x plus 5. This is one term. Okay, this is not a binomial anymore. This is one term. Because we have that radical on the right-hand side, I figure, you know what, let's just square everything and see what happens. So we have a binomial on the left side, which means we're going to do another set of side work so that we can make sure we distribute this properly. And then, of course, what you do to one side, you must do to the other. So we're going to square both sides. We have a 3x minus 9 squared. Let's go ahead and write that out twice just so we can visualize it. 3x minus 9 squared. So let's go ahead and distribute so we can write down what we get. 3x times 3x, that's 9x squared. 3x times negative 9 is negative 27x. Same thing here. And then, of course, negative 9 times negative 9 is a positive 81. That takes care of the left side of the equation. Now, when we square the right-hand side, think of squaring each piece individually, okay? So think of squaring the negative 6. Negative 6 times negative 6 is positive 36. And then think about squaring the x plus 5. Now, keep in mind what this says. Negative 6 times the square root of x plus 5. So when we square each of these pieces of this expression, we want to make sure we keep x plus 5 in parentheses. If that's trippy to you, think about this expression. So when we square it, we essentially square each individual piece. Think of squaring each individual piece because it's not a binomial, it's a monomial. It's a single term, which is what says, oh yeah, this is a 36 and this is an x plus 5, but they're connected by multiplication. And I don't want to forget that I'm actually going to have to distribute. Okay, that's huge. Don't forget you have to distribute. Let's clean up a little bit. 9x squared. This is going to give us negative 54x. Then we have plus 81. And of course, that's equal to, let's distribute 36x plus, did anyone type that in yet? What'd you get when you typed that in?
180.
Cool. So we get 180. Very, very nice. Give me 1 second. I'm going to check something here. Cool. So we get plus 180. And now let's move terms around and see what happens. So we're going to subtract the 36x and subtract the 180. Because we know that since we have a polynomial with degree 2 or higher, we want to set that equal to 0. And then we go through the motions of solving. So subtract 36x, subtract the 180. And let's see what happens. Get rid of this guy, get rid of this guy, is equal to 0. So we have 9x squared. Let's punch this in. Negative 54 minus 36. That's a negative 90x. And then we have 81 minus 180. That's a negative 99. Cool. And once we're here, what should my next step be? What would you do?
Solve with
Yes,
the
how?
factoring.
By factoring? Yep. So what's the first step of factoring?
GCF.
Yes.
You see?
Yeah, awesome. You see it, right? Does everyone see the GCF? It's kind of jumping.
Aye.
off the page.
Yeah, 9.
Actually, no, I think it's three. I think it's like 2.
2 would not work. So we do factor out that 9, divide every term by 9. It gives us x squared minus 10x minus 11. Cool. Then we just factor, which is really nice. I'm so sorry. We need factors of negative 11 that combine to give us negative 10. That's going to be negative 11 and a positive 1, right? Negative 11 times 1, that'll give us a negative 10 when we combine those. So therefore, my solutions are, go ahead and share.
11 and negative 1.
Yeah, score. 11 and negative 1. Recall that we must check each one because we probably do have an extraneous solution, but you want to make sure. So we have the square root of 4, and let's test the 11 first. 4 times 11 plus 5 plus the square root of 11 plus 5 is equal to 3. And let's see what happens. This is 44 plus 5, which is 49. This is 16. Are you already seeing it? Look at this. This is 7. This is 4. Yeah, no, that's no. So that doesn't work, which means 11 is extraneous. Let's try the other one. Square root of 4 times a negative 1 plus 5 plus the square root of negative 1 plus 5 is equal to 3. Let's see if this works out. We have negative 4 plus 5, which is 1. Negative 1 plus 5, which is 4. Cool. 1 plus 2, yeah, that's 3. That checks. So your solution is this set, which holds just negative 1. And that's it. So it's definitely a pretty massive problem. But again, it's totally manageable if you understand the steps involved with solving radical equations. Isolate one of the radicals on one of the sides, and sometimes you have to do both sides, and that's okay. And then use the opposite operation to cancel the square root, which is to square. As we learned last class, if it were a cubed root or a cube root, you would raise both sides to the 3rd power. If it was the 4th root, you would raise both sides to the 4th power. That would just be disgusting, right? But again, it's plausible. We're not going to do anything like that in this class. What questions do you have for me on this particular problem? Okay, I guess that was pretty tame, huh? Let's turn the page and look at some applications. You knew it was coming. Don't even play. You knew we were going to do applications. We always do applications. Okay. The speed of sound, V. One of the things that I really want you to pay attention to is what the heck these variables even mean, right? Think about keeping that in your mind. So V is the speed of sound, and it's in meters per second. Now it depends on air temperature, T. So this is temperature, and it's in Celsius, and can be found using this formula. So V is the speed of sound, and T is the temperature. It says, find the speed of sound. If someone says that to you, find the speed of sound, what that means is they're asking you to find V, right? Because we don't know it. So they want you to find V when the temperature is 30 degrees Celsius. So when the temperature is 30, I always like making little notes to myself. That is, it serves as a reminder of what I'm actually doing. Because we're given that T is 30, it only makes sense to substitute T with 30. So let's plug it in. So V is equal to, the other thing that could happen is you may accidentally write the problem down incorrectly. So just take your time, make sure you're doing this step by step. So 30 over 273. So that's essentially what we have. I would advise you to maybe, you could punch in the whole thing. Let me just show you how you would do this. On your calculator, if you wanted to punch that, you would type in 331.3 times, right? Then we've got the square root. Now, it's really important that you take heed of this set of parentheses because we're going to put the entire expression and then close the parentheses. So 1 plus, and then we have 30 divided by 273, and then close the parentheses. So it sees that it's taking the square root of this entire expression. You don't need another set around the 30 and the 273 because your calculator understands order of operations. It's going to divide before it ever adds. And there you have it. So find the speed of sound. Let's round to the nearest whole number. So we can say the speed of sound is 349 meters per second. Always use and include those units. So let's write 349. So the speed of sound at 30 degrees Celsius is 349 meters per second. I hope you don't mind me abbreviating by just writing the units. Then it says at what temperature. That means we don't know T. Again, it's really helpful to identify what is it you're missing. When the speed of sound is 320 meters per second. So we have V in this case. I'm going to write down the formula, and then I would like you to kind of walk me through what your thoughts are in terms of how you would actually solve this. We have a couple options here, so let's write it out first. V is 320. And then we have the rest of the equation. So 331.3 square root of 1 plus T over 273. Very nice. So I'm just going to call on you randomly just to throw an idea out there. Okay, I don't want you to feel any pressure. If you're not sure, that's okay. Just say you're not sure. It's no big deal. Nung, would you start us off this wonderful, dreary, cloudy, little bit rainy, definitely a little bit cold morning, sweater weather? Why? I don't understand. Nung, what might you do first?
Would you get rid of, like, put 320 on the other side?
Okay, that's an option. Now check this out. If I do bring the 320, and I love that we're talking about this. If I bring the 320 on the other side and I subtract it, then this is equal to 0. But keep in mind that whenever we have a radical in our equation, we want it to be isolated. So technically, it's pretty close to being isolated. So how about we'll leave the 320 and let's navigate a different approach. What do you think, Phil? What do you think we might do? And remember, we're just spitballing. That's all. We're just spitballing.
I want to get the T on the other side, but I don't know if we can do it yet.
Okay. So if we continued on that path, like your eyes are drawn to T, you want to somehow get that alone. If we wanted to continue on that path, what might we have to, I don't know, get rid of?
Yeah, the square root sign.
We definitely have to get rid of the square root. What I may suggest to you all, not that you have to follow this advice at all. It's just going to make your life a little bit easier. Do you agree that this says 331.3 times the square root of all this stuff? Let's just get rid of that 331.3. What operation can I use to get rid of that?
Divide.
Yeah.
Division.
Yeah, because it's connected by multiplication. So we know we always want to use the opposite operation. Let's try this. I want to show you what happens. So if we divide by 331.3, what you do to one side, do to the other, 331.3, notice these cancel out because you're dividing them, right? It's the opposite operation. Let's punch this into our calculators. 320 divided by 331.3. Okay, and it gives me a pretty crazy answer. And I actually think this is okay because we're looking for the temperature, which can be a decimal. Here's my advice to you. I don't want you to have a ton of rounding error. So when I see this in my calculator, I actually am probably going to write out to 4 decimals or 4 places after the decimal, believe it or not. Typically, when you're in pre-calc, when you're in calculus, when you're in differential equations, all those wonderful, wonderful math classes, we typically leave our answers to 4 places after the decimal so that we can minimize error. So that would be my advice to you. Start using the strategy that you'll see students in calculus classes using, okay? So that means I'm gonna write 0.9659. I'm gonna round up. 0.9659. And now that's equal to the square root of 1 plus t over 273. Jose, you made a suggestion. You had commented on the fact that the square root was the issue. So in this case, how would I resolve that? What would I do now?
I know, but I forgot the name right now. Sorry, my mind is not working.
Yeah, that's okay. Can someone back her up?
Square? Both sides?
Yes, we're gonna square. Yes. Yes, we're totally gonna square both sides. Good. So let's check it out. So we are going to put both sides in parentheses. And James, thank you for telling me that. That does help. So we're gonna square both sides like so. Let's punch this into our calculator, because remember the opposite of square root is square. So 0.9659, let's square that side. And again, let's round to 4 decimal or 4 places after the decimal. 0.93, because it's 296, you know what? Let's just leave it. I don't want to round too much. So 5 places this time. It's really not a big deal. Don't sweat that, okay? We're just trying to be as accurate as possible. The square and the square cancel each other out. 1 plus t divided by 273. Super cool. Okay. Someone give me my next possible step. There are a couple options here, which is pretty cool. What might you do next?
Subtract 1.
Yeah, why not? I love that. That's a great idea. That is one of the options we could have taken. So let's subtract 1, bring that over. And I'm just going to move this over here. So we have in our calculator, we'll type that in -1. We get negative 0.06704. Good. And that's equal to t over 273. Okay, last step to get t completely by itself. What do you think?
You could multiply 273 to each side.
Yes, score. We definitely are going to multiply 273 to each side. Very nice. Very nice. So kind of like this, you know, what we used before this strategy. This strategy we learned way back in 098, and it's never going to go away. Like literally, it will never go away. Cool. Take your answer, multiply by 273, and we see, and I'm going to round to the nearest tenths because now we have our final answer. We see that the T, which is temperature in Celsius, is negative 18.3. So the temperature, excuse me, I'm so sorry, is negative 18.3 degrees Celsius when the speed of sound is 320 meters per second. Cool. Perfect. We're done. What are your questions? What's on your mind? What's throwing you off, freaking you out, making you think twice, making you regret being in this class? What's going on? What's that?
Quick question.
Yes.
So when do you know, like, it's generally your time to square? Is it when you have the square root
Yes.
and you can't really do anything else, or?
Yes. So notice, I'm so sorry. I do have water. I'm going to drink some in a second. Notice that here we had the square root isolated by itself. If you wanted anything that's under this square root, you've got to get rid of it by squaring it. Think of it as like the square root is a house, right? and everything's trapped inside that house. You got to get rid of that house to pull the contents out, basically. This,
Okay.
yeah, the square root kind of acts like the P in PEMDAS, that parentheses. You really want to find a way to kind of open that up so that you can use everything that's underneath that radical sign.
Okay, awesome. Thank you.
You're very welcome. That's a fantastic question, because really I want you to think about everything as being trapped until you remove the square root. Very nice. Very nice. So having said that, solving for a variable is going to seem much more tame than what we just did. So take a look. We have v is equal to 3 times square root of gh. Good. And we want to solve for h. That's our goal. Someone shout out what might be my first move. Give me just one idea. What could I do?
Divide 3.
Yeah, I love it. I think that's a great idea. We're going to divide 3 because remember, we're not adding 3, we're not subtracting 3. It's 3 times the rest of this. So if I divide by 3, I'm left with v over 3, notice these cancel, is equal to the square root of gh. Okay, what's our next step?
Don't you want to get the GH alone? So you want
Yes.
to square the
Well,
root.
Yeah, you're right. Square it. So right away, you're noticing we have a square root. We're going to square both sides. I love this. We're going to square both sides. What do you get when you square v over 3? What does that give you? Square each of these. What does it give you?
V squared over 9.
Yeah, score. V squared over 9. That's the power rule, right? Their powers are 1. So it's v to the 1 times 2, that's 2. 3 to the 1 times 2, that's 2. And then you just do the math, v squared over 9, right? Good. The square root and the square cancel each other out, which is super cool. So we have is equal to g times h. And now the only thing is we want to get h alone. How do you do it?
Subtract.
Ooh, am I adding?
Divide by G.
Divide by G. Don't let this freak you out. If you divide by G, okay, I might freak you out right now. If you divide by G, think of it like this. Isn't that the same as multiplying by the reciprocal by 1 over G? Because that's like dividing by G. I just moved it to the side so that you can see it. So instead of dividing by G, that's the same as multiplying by 1 over G. The reason I decided to do this is because then I can multiply this side by 1 over G as well, so that it's not like weird and you're thinking like, where do I put the G, right? So we see that when we multiply by the reciprocal 1 over G, which is the same as dividing by G, these G's will cancel, and then I could put these two together. So that gives me v squared over 9G is equal to h, and then you're done. Okay. Take a look at part B. We want to solve for B. What's the first step? What's the only thing we can do? Say it.
Sure.
Square it.
Square root. Yeah.
Square it, right? We got to square, we have to square both sides. Let me open this up. I'm just going to rewrite this. We have no choice. That b is trapped under that square root sign. So we want to get rid of it first. We want to square both sides. That leaves me with w squared is equal to, and then the square root and the square cancel, so it releases the contents, so to speak. And that's a over b. Cool. What should my next step be?
Multiply it by the reciprocal.
Yeah, that would work. Now, if I multiply by the reciprocal, let's clarify. Are you asking me to multiply by b over a? What may help if I multiply by just
1 over b.
E.
b? We want to multiply by b. Notice if I multiplied, I'm going to put this in, I'm going to write this. Come on, lead. Nope, I don't have it. That's okay. I have scrap paper. if I took that W squared and I multiplied it by 1 over B, I just want to show you what this looks like. These do not cancel. This becomes W squared over B is equal to A over B squared. And then you're like, whoa, okay, let's reverse. If we have W squared is equal to A over B, if I multiplied by B over A, again, I want to show you what this looks like because these are all options. We're not breaking any rules. We're just trying to explore what's happening here. And then it's equal to 1. But I still don't have B by itself. I could progress from here. Or instead, I could say, well, let me just multiply both sides by B. That'll give me BW squared is equal to A. And now all we have to do is isolate B. And we could do that in one step. What's the last step?
Divide by W squared.
Yeah, score. Divide by W squared. This is going to be a lot neater than the alternative. And we've isolated our B. If we wanted to stick with multiplying by the reciprocal, I'm just going to move this for a moment just to show you how we would solve this one. We could again multiply both sides by the reciprocal, but just of this piece. So we would multiply by A over W squared, A over W squared. In which case you see the A's cancel and the W squareds cancel. So you're left with B by itself. And then 1 times A over W squared is just A over W squared. So we could actually use this approach to find the answer. It's just a little bit more involved than had we just multiplied by our denominator, which was B, and then of course, divide by the W squared. Very cool. Very, very nice. I like exploring options just to see mathematically where they lead. And it's okay to do this on your own at home when you're playing around with problems. Okay? Good. Don't fear that. If it doesn't work out and you hit a wall, then reverse, right? Reverse and try a different path. No big deal. I don't want you to freak out about that. Okay, we are ready for the last section of our notes. So this entire section is dedicated to complex numbers. So essentially not the real number system, okay? So we're going to be looking at something called imaginary numbers. Now in a complex number, you're going to have both a real and an imaginary part. Now, just like with radicals, if you had a square root or cube root or any radical in the denominator, you had to get rid of it, right? There's like that special rule where you can't leave radicals in a denominator of a fraction. What you're going to learn is that the same idea applies to complex numbers. If you have an imaginary number in a denominator, you got to get rid of that. Okay, so it's that same concept, that same idea. And I think you're going to find it to be you're going to find it to feel like, okay, I did this already. I understand this concept. The only difference is how we attack that imaginary number, right? The idea of conjugates doesn't go away, which is really, really cool. And then we just have to understand what I actually represents, that imaginary piece. So don't panic. Let's take a look. I think you might like this section a lot. Hopefully, let's check it out. So right off the bat, we know that square root of -4 is not a real number. It's imaginary, right? Because there is nothing times itself, no real number times itself that gives you a -4. That's an issue. What we learned though in the complex number system is that anytime you see the square root of -1, we can actually write that as the letter I for imaginary. Okay, we're going to replace every square root of -1 with an I. So what I wanted to include here for you to know is that if I is the square root of -1, then if I take both sides and I square it, then what that must mean is that I squared is equal to -1. You see, because the square root and the square cancel out. So we've learned that I is the square root of -1 and I squared must be equal to just -1. Okay. What happens here is if you have, for instance, a real number, like I'm going to show you this one in a second. What happens here with the square root of a negative number is that you want to take out the factor of I first, right? And then you're left with the remainder. Let me show you what I mean. With the square root of -4, you actually want to break this down into the square root of -1 times 4. The reason for that is because we know that the square root of -1, and I'm just going to kind of like circle it like this with my highlighter. The square root of -1 is I. And then we have the square root of 4. But the square root of 4, since this is a perfect square, is 2. So this leaves me with 2i. That's essentially how we would progress if we ever had a negative square root. We would understand that it's a complex number, that it has an imaginary part, and we would rewrite it so that we include that I in our expression. Just hold on to that idea. So when writing a number like a radical and I, you have a real number and you have an imaginary number, and that essentially puts together your complex number, so to speak. So when you write your complex number, you always want it to be in the form a plus bi, where the real part is a and the imaginary part is b, right? Because this bi piece, this represents your imaginary part. Hopefully that makes sense. Some examples of complex numbers that have radicals: 3i squared to 5, that's an example. 3i, I squared to 5, 3. So these are all ways to represent a complex number, especially when you have like a radical or something like that. Okay. But what we want to practice doing moving forward is we want to practice writing our expressions in a plus bi form. Okay. A plus bi form. That's really, really important. I want you to kind of hear that in your mind again and again and again. A plus bi form. Okay. Let's look at our first expression. And as we do these more and more, we're going to end up skipping a tiny step. I'll show you what that is in a moment. So we have 3 plus the square root of -16. So first off, I want to show you that this, go ahead.
Move the page up.
Oops, I'm so sorry. Thank you. I want to show you that this square root of -16 is the same as -1 times 16, right? Where this piece, this square root of -1 is I. So we have 3 plus I, but we still have that square root of 16. I'm breaking this down piece by piece, but in a little bit, you're going to end up just jumping to the solution, which in this case is going to be 3 plus, well, square root of 16 is 4. And so it's 3 plus 4i, a plus bi form. This is your final answer. I'm just going to write underneath it, a plus bi. That's our goal. And there is your complex number. Let's do it again. We have 5 minus,
Professor.
yes, go for it.
So I is the imaginary number.
Yes, I is the imaginary number, and I specifically is always just the square root of -1.
Okay.
Always, 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 always. So for instance, Jose, when you see this square root of -12, you already know you're going to take an I out, right? So essentially, I would look at this as 5 minus I square roots of 12. Do you agree?
How about if we don't have negative sign?
Oh, if you don't have a negative sign, then you just go through the process of breaking down a radical as normal. So you just go back to our previous section where it's just simplifying a radical. Excellent question. This I only applies to an even root. In this class, we're only going to look at square roots. So if you have a square root with a negative radicand, that's when you take that I out. Okay, because remember, square root of -1 is I. So that takes care of that square root of -1 piece. We do have a square root of 12, which we can break down. So let's kind of move through this. We have 5 minus I, and then we have 4 times 3. 4 is the perfect square. Okay, and then when we go ahead and write this out, we know that square root of 4 is 2. So I can write my answer as 5 minus 2i square root of 3, a plus bi form. Any questions on this format? Okay, hopefully you're not freaking out. Our next example is just the number 4.
I'm sorry, I had a question.
Yes, awesome.
Um, I'm so confused why it's 5 minus 2i and not 5 plus.
Oh, because of this sign.
Oh, I'm sorry.
That's okay.
Okay.
No, that's okay. It's really important for us to dissect this completely. Because we have 5 minus in this expression, that minus, that plus, that's not going to change. By pulling out that I, this I is like a card, right? And on the other side of this card, it says square root of -1. So that has nothing to do with the sign that separates your terms. That's a great question to ask.
Okay.
Awesome. Thank you. For our number 4, just plain old 4, you're like, 4, what can I do with this 4? Remember, we just want to write it as a complex number. And we want to write it in a plus bi form. Well, that's a real number. So that must be the real part a. So when we think about writing this in a plus bi form, there is no imaginary part. So we would write our 4 as a complex number as 4 plus 0i. That's how you would write it as a complex number, 4 plus 0i. Would you ever really do that? Probably not. Is somebody going to say, hey, can you write this 5 as a complex number? Okay, but probably not. You're probably going to have something a little bit more complicated that you'll have to work with.
Why would you put the 0 there instead of just the B itself?
Oh, because B is 0 in this case. The reason B is
Gotcha.
0 is because there is no imaginary part. Right? Think back to something silly. Think back to, let's say you were graphing a line, right? And let's say you had y is equal to 3x, but you wanted to graph that. You recall from graphing that the slope-intercept form is y equals mx plus b. So what some of you may do is you would say, well, I would just write this as 3x plus 0, because then I know that my y-intercept is 0, 0, and my slope is 3 over 1. So that means you go up 3 over 1. And then, of course, you make your line, right? Do you remember this, Jimmy?
Yes.
Good. So we use, you're like, oh, too well. So we replace the b with the 0 because it's a placeholder. And it also represents that 0 is my y-intercept. Same idea with this concept. We use 0 as our placeholder for our imaginary parts because we don't have one. So we call it 0i. I will tell you again, you're not going to see this very often. They're not going to ask you to turn a real number into a complex number. Okay?
Okay, thank you.
You're very welcome. Square root of -9. How would I rewrite this? Keeping in mind, I know what I represents. How would you rewrite this expression? What's square root of 9?
3.
Right? And what's the square root of -1?
I.
Okay. But we want to write in a plus bi form. So if we're thinking of a plus bi form, this is going to become 0 plus 3i. Do you see the placeholder here again? A plus bi. The only part that existed in this complex number was the imaginary part. So we use 0 as our placeholder, a plus bi. Let's do it again, square root of -18. The first thing I would do if I were you, I would take the I out. Okay, would you please break down the square root of 18? What's my largest perfect square factor?
Nine and two.
Yeah, perfect. 9 and 2. And then we say, okay, well, I know the square root of 9 is 3. So this becomes 3i square root of 2. And because this is just the imaginary part, we want to write it in a plus bi form. You always want to write in a plus bi form. So we have 0 plus 3i square root of 2, and there you're done. What are your questions for me? Okay, hearing none, let's turn the page. So obviously, if we start by understanding how to rewrite expressions in imaginary form, we're now going to perform operations, okay? So let's add or subtract. First off, look at step number 1. Always, always, always replace all square root of negative n with I square root of n. You always want to replace first, okay? Very, very first step. Then you add the real parts together, you add the imaginary parts together, and then you write your answer in the proper form. Cool. Notice we have 4 plus 13i. And then we have minus 6 minus 8i. So I'm just going to write it out like that first. We know we were adding these 2 sets of parentheses, so we don't have to worry about changing any signs. Now, all we have to do is keep in mind our goal, which is a plus bi. That's the goal. So we want to combine the real parts first. 4 minus 6, which is negative 2. And then we want to combine the imaginary parts, which is 13i minus 8i. When you combine these two, you get positive 5i, and then you're done. Cool, right? Now, yes, Jimmy.
Since the second, oh, I mean, you're gonna get into the second one, so I'll wait.
Okay. Okay, all right. So with part B, notice we actually do have square roots of negative numbers. What I would advise you to do is use like the side of the page to do a little bit of side work to change each of these. So for instance, I would convert square root of negative 8 into an imaginary term, and I would also convert square root of negative 18. I would clean both of those up real quick. First off, we're going to take I out because it's a square root of negative 1. Then we're going to break down square root of 8. That becomes 4 and 2. Excuse me. And then we'll actually do this. So square root of 4 is 2, so it's 2i square root of 2. That's what that square root of negative 8 becomes. We'll replace that in a second, not yet. Then we have square root of negative 18. Same thing, let's take the I out. Are you seeing this pattern and starting to develop a flow here?
Yeah.
Awesome. 18 is 9 and 2. Square root of 9 is 3.
Was it? Yeah.
Yeah, 3i squared to 2. Now, Jimmy, would you do me a favor? Tell me how to put these back in instead of these guys. So what would my expression be?
6, 6 minus, would you do parentheses?
We could, but we actually don't need the
Or
parentheses
no?
because he's just subtracting it.
Or it'd just be 2i square root of 2 then?
Awesome. Keep going.
And then minus parentheses 4 plus 3i square root of 2.
Yes, beautiful. So we just replaced those two pieces. We cleaned it up. Now they have that I piece, which is beautiful. Notice we're subtracting. What do I have to do with this negative? Remember back to what we did whenever we subtracted polynomials or expressions. What would I do with this negative sign?
Distribute.
Yeah, distribute. We're going to distribute to each term. And that'll allow us to open up this entire expression. So 6 minus 2i squared to 2 minus 4 minus 3i squared to 2. And now we combine like terms, real parts and then imaginary parts. Notice our real parts, 6 minus 4, that's 2. And then notice negative 2i squared to 2 and another negative 3i squared to 2. These are completely identical, which is awesome. So it's going to give us negative 5i squared to 2. And there you have your final answer.
Just a quick question.
Yeah.
So the only thing that's giving me a little bit of confusion is when we're doing the imaginary numbers and the square root,
Yes.
like the last part, doing it. Go.
Like this?
No, yeah,
Oh,
we go up on the page.
yeah.
You know how we went down in order with the square root of the numbers?
Yes.
The last part with the highlighted is where it's
Oh.
like, I don't get how the end product of it
Oh,
goes into
becomes
that.
like 2i squared to 2.
Yeah,
Oh, okay, okay. So recall, let's pretend this I isn't there, right? And I'm just gonna cover that up. If you just had the square root of 8 and you said, well, square root of 8 breaks down into square root of 4 times 2, because you always want to break it down into a perfect square and the other factor. Wouldn't you say that this becomes 2 square roots of 2?
yeah,
Okay, so the only thing, Jimmy, that you're adding is that I. And we always want to put the I after the coefficient, but before that radical. Because if I put it afterwards, people might think that the I is in the square root, which is a huge issue. So we always like putting it kind of like in front of the radical, but after the coefficient.
Mhm.
That square root of 4 is here, which is 2. And then you just bring that over and square root of 2 is left over.
so you're breaking down the 4 and then just dropping it on the 2 and
Yes.
adding the I.
Yes, yes, you have to. Always,
Okay.
if you want, think back to how we simplified radicals. And like, for instance, this one would be 3 square roots of 2. And we have that 3 square roots of 2. The only thing we introduced was that I.
Gotcha. Okay.
Very nice.
All right.
Very nice,
Thank you.
very nice. You're welcome. Good. That's pretty much the extent. Like either you're going to have your expression with the imaginary numbers already in there, those I's, or you'll have to write the imaginary numbers in there and then do the math. Okay. Let's look at multiplying complex numbers. This is fun. I swear it's not a big deal. The steps don't change. Look at step number 1. Replace all square root of negative n with I squared of n. This is your first step. You got to do it first, okay? Please don't skip this. If you do, your answer will be wrong. Obviously, you want to distribute to drop parentheses. And then here's the cool part. After you distribute to drop parentheses, anywhere you have an I squared, replace it with a negative 1. Then do the math, combine like terms, and write your answer in A plus BI form. Let's check it out. This first one is nice because it's already done, right? You don't have any square roots of negative numbers. So we have 3i times 5 minus 2i. So let's go ahead and distribute. 3i times 5 is 15i. 3i times negative 2i is negative 6i squared. Right? Because I times I is I squared. Think back to when you multiplied x's, right? X times x is x squared. Right away, I see that because I have an I squared here, I want to replace that with a negative 1. So I have 15i minus 6 times negative 1. And then we're like, oh, okay, well, I can do that. That gives me 15i minus 6 times a negative 1, or negative 6 times negative 1 is a positive 6. This is not A plus BI form. This is reverse. So you want to flip the order and write your answer in the proper form. So your answer is going to be 6 plus 15i, A plus BI form. What did you think? Not bad, right? Not terrible. Okay. Would somebody tell me what's the square root of -4?
2, negative.
Not -2. We have the square root of a negative number. So what is
I. Do I?
2i? There we go, 2i. Think back to this idea. Square root of -4 is the same as square root of -1 times 4. Remember that the square root of -1 is I. And the square root of 4 is 2. Okay, does that help, Jimmy?
Yeah.
Good, always take that I out. Here, how would I rewrite this? I have square root of -2. What's the only way I can rewrite this?
I √2.
Yes, I squared root of 2. Very nice. And then we have +7. Good. So we've converted each of them first. Now we're allowed to distribute. 2i times I squared to 2 is going to be 2i squared square root of 2. You're just putting it together. And then 2i times a +7 is +14i. We see that we have an I squared. I squared is -1. So it's 2 times -1 squared to 2 plus 14i. And then we'll just do the math. 2 times -1 is -2. So -2 squared to 2 plus 14i. A plus BI form. Do you want to try part C on your own and see how that goes? Let's do it. I'm going to give you just a few minutes. Go ahead and try this on your own. I'm going to pause the recording. Oliver looks at me like I'm crazy. I am. Okay. We already know what the square root of -8 was because we so brilliantly wrote that at the top, right? The square root of -8 is 2i squared to 2. So I'm just going to replace this. So we have 3 minus 2i squared to 2. That takes care of that. We also know what the square root of -2 becomes because I wrote it right here. All we have to do is take that I out. So it's I squared to 2 plus 5. We have the product of binomials. No big deal. We use the same process we did when we had, binomials that we are familiar with. We just distribute. So we start with the 3, and then we move to our next term, right? We do the same exact process. 3 times I squared of 2 is 3i squared of 2. Don't overthink it. 3 times +5, +15. This part is the part that's going to annoy some of you, and I apologize. But I actually kind of find this fun because I'm crazy.
Would it be 3i
Where?
over 2 when you distribute?
Yes, right here. You mean these two?
Yeah.
Yes, 3i squared to 2, exactly.
Okay.
Yeah, you're totally right. And then we get the 15. But now let's distribute the -2i squared to 2 times I squared to 2. Okay. This I actually feel like it would be worth writing down. -2i squared to 2 times I squared to 2. First off, we have our -2. We have I times I is I squared. Square root of 2 times square root of 2 is square root of 4, which is 2. Square root of 2 times square root of 2 is 2. So then we fix this. -2 times 2 is -4. And then we see that we have an I squared. And we know that I squared is -1. So -4 times -1 is a +4. And I'm going to go ahead and write that down here. This is why I love doing side work, so that we don't clutter up the space like crazy. It gets too messy too quick. And then we distribute the last piece. So -2i squared to 2 times +5. That's going to give me negative 10I square roots of 2. So negative 10I square roots of 2. Combine the real terms first. 15 plus 4, that's 19. And then combine the imaginary terms next. We have 3I squared to 2 minus 10I squared to 2. So that gives me negative 7I squared to 2. Who had that expression? Did anyone have that? Okay, that's okay. That is okay. That is totally okay. Like, don't worry about that. The more practice you have, the better you're going to be at this. Where were some of the issues? What was the weird part? Would you be willing to share? What was the weird part?
I honestly split up the eyes wrong.
Oh, okay.
That was my biggest thing.
Okay. Okay. And that really does take practice. The more you do, I swear, the easier it'll get. In terms of like making sure you pull that I out and then simplifying the radical, that kind of thing. Did it go haywire anywhere else? I have a feeling it might have been
It
this.
was just, I think it's just the I, because I eventually got, I guess, 3 out of the 4
Oh,
parts with it. Like I got the 3I square root of 2 plus the 15, and then I got the 10I square root of 2.
this one.
And then I just didn't know what else to put there.
Yeah,
So I'm
this,
just stuck with like a incomplete equation. I'm like,
yeah, this one is tricky because there's so much going on here. That's why it's going to be helpful from now on. Write it like on the side somewhere, just so you could see it all, because it's a lot easier if you see it all. Did this breakdown help, Jimmy?
yeah, it's still a little weird to me. I don't know, but I'm getting there.
Good. I love it. I love it. I love it. I love it. Good. More practice. You guys are going to be awesome at this. I want to finish these last 2 pages. This is it, 1 and 2, before we take our break. Okay. So we're almost done. We are now ready to talk about conjugates. We already talked about this when we rationalized denominators. Remember, it's the same expression, just with the opposite sign. So the conjugate of a plus bi is just a minus bi. Okay. The conjugate of 3 plus 4i is 3 minus 4i. The conjugate of 2 minus 5i squared to 3 is 2 plus 5i squared to 3. That's it. We just wanted to write down the conjugates. For part B, now I want you to multiply 3 plus 4i by its conjugate. So let's take 3 plus 4i, if I can write it, and let's multiply it by its conjugate and see what happens. So let's distribute. 3 times 3, 9. 3 times a negative 4i, negative 12i, right? We're going to keep that in there. What do we get here?
And
There's 12i.
Yeah, positive 12i. And then what do we get this last piece here?
would be a negative 16i squared.
Yes, awesome, negative 16i squared. Okay, cool. First things first,
Then you
notice,
combine like terms,
yes, what do these do to each other?
cancel each other out.
Okay, that's pretty cool. Those are gone. That's an interesting feature of complex conjugates, by the way. Those inner terms, they always cancel. I squared is
Negative 1.
negative 1. So then
So
we
it just
have, go ahead.
turn to 16.
Yes, it turns into a positive 16, which means my answer is 25. Look at what happened. We took a complex number, we multiplied it by its conjugate, and we ended up with a real number. That will always happen. Mark my words. Okay, that will always happen. Your inner terms will cancel, you won't be left with an I, which is why we use a complex conjugate to make sure we don't have any imaginary numbers in the denominator. Cool, we're now ready to divide. Okay, same idea, excuse me, this never goes away. Always fix all your square roots of negative, whatever a number is. Okay, always fix it. That's the first thing. We want to rationalize the denominator by multiplying both the numerator and denominator by the conjugate of the denominator. And then we want to write our answer in a plus bi form. Okay, cool. All right, the conjugate of a positive I is a negative I. So we're going to multiply by negative I over negative I. Okay. Next, we are going to actually distribute. So I know this negative I is on the right, no big deal. Let's just distribute. 4 times negative I is negative 4I. I times negative I is negative I squared. All over, I times negative I is negative I squared. Everywhere you see an I squared, everywhere you see I squared, you're going to replace it with a -1.
This is gonna end up being negative 4i.
-4i, replace this with a -1. What does that become?
Plus 1.
Yeah, good. And of course, all over, when you replace that with a -1, it's going to be a +1. So you're totally right. So out of curiosity, Shane, what's the appropriate way of writing my answer?
Negative 4i plus 1.
Oh, fix it. A plus bi.
Oh, I'm sorry. 1 minus 4i.
Yes, that's your final answer. Good. A plus bi form. Sometimes it just helps to write that right underneath. A plus bi. Good. Take a look at part B. What is the conjugate I'm going to multiply by?
Negative 2 plus I.
We can actually leave the 2 as is. You could just do 2 plus I. That'll work because you just
Yeah.
want to change the sign in the middle. So let's do that. Let's multiply by 2 plus I. Put parentheses, that's going to help. All right, very nice. Kim, would you distribute the numerator for us? Tell me what you would get if you distribute.
You would get, hang on a second, I'm still like working on it on my
Yeah,
my
sure.
paper.
Yeah, that's okay. And honestly, just if you want, just walk us through just this part. Just multiplying this part here.
12
Uh-huh.
plus plus 6i
Yep, awesome. Plus 6i
minus 10i
minus 10i
minus I squared.
minus 5i squared. Cool. Very, very nice. Let's take care of the denominator before we do anything. Summer, would you distribute the denominator for us? So we have 2 minus I times 2 plus I. Would you go ahead and just distribute that for us? I'm drawing the lines of distribution, but I'm like squeezing them in there. Okay, go for it.
It's okay. So would it be 4
Uh-huh.
plus I,
Ooh, plus,
or wait, sorry. I think I'm getting my lines mixed up.
that's okay.
So 4, oh, sorry, yeah, and then plus 2i,
Awesome.
and then minus 2i,
Beautiful.
and then minus I squared.
Yes, awesome, awesome, awesome. Okay, everywhere we have an I squared, I'm just going to circle it. Because I want to make sure that we keep in mind that these always turn into -1s, right? Good. The next thing I'm going to do is I'm going to notice these two terms cancel each other out. So those are gone. And then if this becomes a -5 times -1, then that means this becomes +5. Are you all okay with that? This is +5. So we have 12 plus 5, which is 17. Then we have 6i minus 10i, which is -4i. And in our denominator, we have 4, and then a negative times a -1 is a +1. So 4 plus 1, which is 5. This answer is actually not complete. The reason it's not complete is because we need to write in A plus BI form, which means, Tiana, no worries, I hope you feel better, which means we're going to split it up into two fractions. So our first term is 17 over 5, and the next term is 4i over 5, A plus BI form. That's what you're looking for. Please don't forget that. Any questions on this? What are your questions for me?
Can we just go over how you got the 17 again?
Yes, yes. What I ended up doing, and I should have written this down. What I ended up doing is, do you see here somewhere how we have -5 times -1, and then that just becomes a +5?
So did you take the -1 from the sign in front of the 5? Is that where you took it from the I squared?
Yes, I squared is a -1.
Right, okay.
So because I squared is a -1, then -5 times a -1 is a +5.
Okay.
And then that's why I'm saying, oh, okay, well, if this is +5, then 12 plus 5 is 17. That's how I got that guy.
Okay, that makes sense.
Excellent. Great question. What other questions do you have for me? What can I help clarify? Okay, hearing none, let's take a look at part C. This square root of -5, how would I rewrite this using an imaginary number?
I square root of 5.
Yes, beautiful. So we have 2 over 3 plus I squared root of 5. What is the conjugate of my denominator?
3 minus I square root of 5.
Yes. You are all doing excellent. Yes, that's exactly correct. Let's go ahead and put these bad boys in parentheses and let's distribute. So we get 6, right? Because we're distributing just here, minus 2i squared root of 5. So there's the numerator. That's all done. The denominator, again, is going to be a little bit of a pesky situation here, but let's just, navigate carefully. 3 times 3, that's 9. Now recall that 3 times -I squared root of 5 is a -3i squared root of 5, and we have positive 3i squared root of 5. So these two terms will cancel each other out. Is everyone okay with me not writing it down because I know they're just going to cancel anyways? Are you all okay with that?
I'm okay with that. That's okay.
Okay, beautiful. So then all that's left is to multiply I squared root of 5 times -I squared root of 5. This gives me negative I squared square root of 5 times square root of 5 is 5. We know that I squared is -1. So what does my denominator become when we do all the math?
Negative. Wait, no. Would be 8.
Well, what does this become?
5i.
Well, the i's gone, which is cool. It's because it was a -1. This says 9 minus a -1 times 5.
-5.
This would be a -5, true. So now we
Yeah.
have 9 minus a -5, which is?
+5.
Yes, 9 plus 5. So 9 plus 5 will give us, and actually I'm going to write this out. This is 9 minus -1 times 5, which is 9 minus a -5, which is 9 plus 5, which is 14. I'm doing a little bit of side work here. So we have 6 minus 2i squared root of 5, but each of these are over 14. We are not allowed to write this as one whole fraction. What's the last thing you notice about this expression? What do you see here that you can do?
square root?
No, the square root's fine because it's not in the denominator, so that's okay. Take a look at the first fraction, 6/14.
Or you could reduce it.
Yes, you can. So we're going to divide out a common factor of 2. So this becomes 3/7 minus, what about over here? Can we reduce again?
-2 and 14.
Yes, these definitely reduce. 2 goes into itself once and into 14 7 times. So we've got 1i squared to 5/7. And that's your final answer. You don't need the 1 there. I just wrote it, but you don't need it. You could just write 3/7 minus I squared to 5/7. But you've got to split it up. It must be a plus bi form. Get used to splitting it up. Awesome. We have only one section left, and all it is talking about the cycle of I. So let me show you. It's super easy. So check this out. I to the 0, anything to the 0th power is 1, right? We learned that a long time ago. I to the first power is still I. I to the second power is -1. And I to the third power is -I. Then check this out. If you had I to the 4th power, that's the same as I to the 0th power, which is 1, because this actually runs in a cycle. So I to the 6th, I to the 7th, I to the 8th, 9th, 10th, 11th, and it keeps going, keeps going, keeps going, keeps going, keeps going. So let's go ahead and fill out the powers of I here. I to the 0 is 1. I to the first power is just I. You're not changing it. We learned that I squared was -1. And then I to the third is simply I squared times another I, right? That's what gives you I to the third. Well, -1 times I is a -I. When we think of I to the 4th, we can say, well, that's the same as I squared times I squared. Well, -1 times -1 is +1. Do you see how this cycle is repeating? So 1, -1, -I, +1. It goes through this same process. To figure out what I is to any power, all you have to do is divide by 4 and just note what the remainder is. Okay? If the remainder is 0, it's like I to the 0, which is 1. If the remainder is 1, it's like I to the first power, which is I. If the remainder is 2, it's like I squared, which is -1. And if the remainder is 3, it's like I to the third power, which is -I. So let me show you 4 problems and then we'll take a break. I to the 35, please take your calculators. Right, if we essentially divide by 4, we get 8 3/4, right? So essentially we notice that 4 times 8 gives us 32. And that leaves us with 3 powers of I. Because the highest we can get, the highest multiple of 4 is 32. That's smaller than 35. So if we have 3 left, then we could say, oh, I know what I to the third is. I to the third is -I. So that one's done. Divide 80 by 4. Do you see how it goes in evenly? 80 divided by 4 is 20. It goes in evenly, which means there is no remainder. Okay, no big deal. I to the 0 is just 1. Let's look at 77. Let's divide this by 4 just to see what's happening. And it's 19. So let's take 19 times 4. That gives us 76. So 76 is the highest multiple of 4 that we can have, which means there's 1 left over. And I to the first is just I. Do this last one. Do this last one really quickly. And then when you're done, go ahead and type into the chat what the answer is to this problem. Yes, Nung, that's perfect. Let's see a few more guesses. Kim, that's perfect. Oliver, that's perfect. Let's do one more in the chat. And then we'll go on break. Shane, beautiful, cool. So we know that the highest multiple of 4 is 104. So that means we had 2 left over. And I squared is -1. Yes, Jose, beautiful. Zach, excellent. And you're done. Very, very nice. We are all finished with unit 3 on our 5-minute break right now. I'm going to scan all these notes and I'm going to put it into Lumen. In the meantime, I'm going to leave and come back into our Zoom meeting. So Jeff, I'm going to put you in charge for the 5-minute duration. And that way it actually separates the videos. And then when we come back, we will start unit 4. All right, I will see you all in 5 minutes. So let's meet at 10:30. See you at 10:30.